Hi and welcome to video 5 on this statistical inference topic, Unit 4 Topic 3 of Specialist Mathematics. And in this video we're going to be talking about the distribution of the sample mean for any random variable. So we've just been talking about normal distributions and the sample mean from a normal random variable, but now we're going to talk about any random variable. So you remember in math methods we've talked a bit about the fact that sampling from any set of data that has follows some form of pattern, if you take a large enough sample, then it will be approximately normal. It's generally recognized that large enough sample number is greater than or equal to 30, and that's quoted in the syllabus, so you can use that, except for the binomial one, which is NP has to be greater than 5, NQ has to be greater than 5. But once you get out into working with this in the real world, depending on what you want to do and what you're using it for, if you're looking for just a general understanding of the feelings of a group for a political survey or something, well, n is greater than or equal to 30 is probably fine. Whereas if you're taking samples of bolt strength that you plan to use to build a bridge across a river, you might want to have as much confidence as possible, and therefore your samples might be a bit bigger. So anyway, take that as you will. Probability distributions, just a reminder, we have a binomial distribution, it's discrete, but even a binomial distribution will follow some central point and then drop off on either side, so you get something that looks fairly normal. A uniform distribution, I've done the one that's the obvious dice roll, it's the one where every outcome is equally likely, so you get this flat distribution. An exponential distribution, which you've been doing in Specialist before. So this is a probability and it's a random variable with an exponential distribution. And then we have other, I've just drawn some weird and wonderful shape there. And it could be any distribution as long as the area below is equal to 1. Now, the sample mean, and it doesn't really matter what you get. So if your random distribution sort of looks like this, you will still have a sample mean. And so the mean might be here. And you'll still have a standard deviation of this set, even though it might not really mean a great deal. But when you are taking samples, you'll be getting samples where the sample means are close to mu, depending on the sample size. So yeah, you might get a mean of the sample out here or down here, but most of them are going to be around here. And so what happens is your sample distribution of means will come out as normal, and that's kind of the idea of this topic. And in fact, that's the idea of the central limit theorem, which you may see quoted again in your exam, and you may see me call it the CLT, the central limit theorem. The CLT states that for any probability distribution with mean of mu, standard deviation of sigma, where the sample size is large enough, the distribution has a sample mean distribution that will be normal, as we've just spoken about. So this is the step-by-step process, just to build a bit of understanding. If you get a distribution, any distribution, and it's got a mean of mu and a standard deviation of sigma, and you sample it n times, so you might take a sample of 10, and then you find x bar, so the mean of that sample. Now if you were to repeat that, step 2, heaps of times, say 100 times, you will form the sample mean distribution. So you would have 100 values that represent the average of a sample of 10 100 times. And you would expect that to be normal. Occasionally your sample of 10 might give you an offhand result, something you didn't expect. That may happen occasionally, but mostly a sample of 10 is going to give you some nice central result. And of course this all depends on it being a random sample with no bias, so keep that in mind. And then we get this result. The sample mean will have a standard deviation of this and a mu of an expected value of mu. Now the standard deviation is related to the sample size. So as you increase the sample size of x bars, so the number of times you sample, you take a sample of 10 or whatever, as you increase that, you will increase your the compactness of your normal distribution, which is loosely interpreted to the accuracy of your results. So let's have a look at an example. And just keep in mind here, of course, you're not often, in your case, you're probably not actually going to be doing the sampling. We're just talking about the math behind it and looking at probabilities behind that. So example 3, and I've actually done the solutions of these. It's a bit of mucking around and I didn't really want to waste time doing previous stuff. So I'll talk through the solutions. So in example 3, a probability density function follows the distribution shown. So f of x, and this is just stolen from one of the math methods exercises. So I know it works. If you wanted to test if this works, you just have to check that the area between 0 and 2 of this function was equal to 1. Because the area has to be 1 under a probability distribution, and anywhere below 0 or above 2 on the x-axis has a probability of 0, so it's all the actions between 0 and 2. Determine the probability that the average value in a sample of 50 is greater than 1. That's what the question is asking. The average value in a sample of 50 is greater than 1. So this function here, it's a quadratic, which means it's not quite normal, but it's not too dissimilar in shape. It's got a continuous x-axis, and it goes from negative infinity to infinity, but remember all the action is between 0 and 2, and because it's quadratic it passes through 0, 0 and 2, 2. I can see there the two intercepts. It goes up to some value, I don't know, it doesn't really matter too much, and so I know the area under that quadratic will be equal to 1, and I want to know what is the probability if I take a sample that sample will be greater than 1. Now the mean might be 1, it might not be 1. This may have an answer of 50%, it might not, so just be careful. And as I take more samples, then I get a better approximation. So the first thing we need to know is we need to know the population mean, and we need to know the population standard deviation. So keep that in mind, that this all depends on this value and this value in order to be able to use that value to get the sample mean and sample standard deviation. So the population mean, going back to our work in math methods, is equal to the integral between 0 and 2 of the function times by x. That's how we get our expected value, and I've just done this in a graphic calculator because it is a math method skill, and it's 16 over 15. So my actual expected value is just above 1. So that's the first thing. Then our expected value squared is going to be part of the process of finding our variance. So this is a really typical set of working out. To do the expected value of x squared, I just put in my x squared instead of x, but my function remains the same. I get 32 over 25, but my variance is equal to the e of x squared minus e of x all squared, which gives me this, and that gives me that variance. So I've now got a variance and I've got my mean. And these are just for the standard probability density function. So that's just for my density of x. So I'll just put a little summary of this here. Variance of x. So this is 16 on 15 and this is 32 on 225. But I've also got x bar, which is my sample mean distributions. So what if I took x, sampled it heaps of times, and then looked at the distribution of possible x bars of my samples, and that's what this is. Now we've already discussed that it's the same mean. That should still center on the same value. It's the variance that's affected. So if I have a look here, I've got the same mean, that's my variance. Variance and the standard deviation of x that's affected. So that's 4 root 2 over 15. Now, step 2 is to determine the sample statistics. So e of x bar, they're equal, but my variance is affected because I've got to take n in now. So I've got my variance and my standard deviation from the previous question. So this shouldn't be variance, it should be standard deviation, which is that one there. And I use 0.377, but it's 4 root 2 over 15. And when I divide 4 root 2 over 15 by the square root of 50, it turns out I get 4 over 75. So I get 4 over 75, which will be root 50 times smaller than the original standard deviation. Now, if step 3 is to assume normality, which we can do, and n was greater than 30, so that's great, and then calculate the probability. And we want to know the probability that the average value, so that's x bar, in a sample of 50 is greater than 1. So I go down here, I want to calculate the probability that x bar is greater than 1. So it's an NCD between 1 and 2, 2 is my upper bound, and then 4 over 75 is my standard deviation calculated here, and 16 over 15 is my expected value, my mu calculated earlier, and my calculator spits out about 0.8944, or 89%. And that kind of makes sense, because if I go back up here, again, I had my expected value here just slightly bigger than 1, but because my sample of 50 was reasonably large, I get a fairly compressed set. So my normal distribution for the results of the sample might look like this. And you can see how 89% would fit in there because it's just this tail that's not counted, and that's about 10%, 11% of it. So there's that example, a fairly tough example, but again, it's just based on some substitutions into known formulas now to complete these samples and some interpretation skills. There's a little bit of a special case of the binomial distribution. Just keep in mind that we get our mu and our sigma slightly differently, so we don't have to do that integrating for the binomial distribution, and it's the same with the uniform distribution as well, though they don't really come up quite as much. So for binomial, to get our mu and our sigma, we have to do these calculations, but then when we take the samples, we still get that the expected value of y bar is equal to p, which was our expected value of the original as well. So p is our expected value in both cases, but the variance is equal to p times 1 minus p over n, and the standard deviation is equal to that. So we do get a slightly different standard deviation and variance in both cases, but you'll notice here that we still get that over root n. So here's my example 4. In a population of school students, 90% of them passed an exam. What's the probability in a sample of 40 students at least 85% of them passed? So this is a sample n of 40, and we need to find our expected values and our standard deviation. Now the expected value works exactly as you expect. It's binomial though, so we have a p-value. It should be between 0 and 1. We've taken that straight from the question. My standard deviation is just p times q over 40. And that sample size again, as that increases, it decreases my standard deviation. So I get a fairly low standard deviation. And then it's just an NCD question again. 85% is my lower bound, 1 is my upper bound. There's my standard deviation, there's my mean, and I get 83.66%, which is what I expected because 0.85 is about 1 standard deviation below the mean. So I'm fairly happy with that. We are concerned, it says here, what is a concern? We are concerned because whilst we have got a sample of 40, i.e. our sample size is greater than 30, that's great, but in the binomial we also want NP and NQ to be greater than 5. But our NQ in this case, deliberately set up to be, is not greater than 5. So it's maybe a little bit skewed for us to be making these estimations. It's pretty close, and it's generally speaking, even pretty close is going to be good enough, and we can give an answer, but it just lowers our confidence in these results. And we're talking about statistics and probability, so it's never ever perfect. It's always about how confident are we in our results. So there's exercise 15E, and we've talked a bit about how we'd apply this idea to non-normally distributed sets for sample means. And so you can be working on 15E. All the best.